Another special product is this perfect square trinomial. PS, I tend to use PST, so I don't have to write it out every time as a shorthand for perfect square trinomials. There's a couple of things you need to be looking for. First of all, a little NTS, note to self, look for two perfect squares on the ends. And then we're just going to assume that it is a perfect square, and then we check if it really isn't. So by that, I mean, like, look, I'm going to look at the ends of this, and I can give you some advice. I would make a list of all of the first 20 perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9, so that your eye gets trained at recognizing perfect squares. That would be my advice. You don't have to do this, but you do have to be able to recognize. Like, if I looked at this one, the first one, I'm a perfect square, and so am I. They should be screaming at you, I'm special here. So when you have a trinomial like this, I'm actually going to just assume that it is a perfect square, and then if it isn't, then I'm going to correct it. So I'm going to say, okay, I think it's a perfect square binomial. That means it's a binomial raised to the second power. Take the square root of the first term, then take the sign in the middle and the square root of the last term. And the way you check is take product of terms and double to see if product is middle term. If it is, that means you're done. You don't have to do any more. So if I take the x and the 3, negative 3, so x times negative 3 is negative 3x, and double, I get negative 6x. Is that the middle term in there? If the answer to that is yes, you are done. You have factored correctly. If the answer is no, you're going to erase what you just did and try something else. So if you look at the next one, I'm a perfect square and so am I. It should scream at you, okay? And for it to be a perfect square, by the way, the variables also have to have exponents that are multiples of 2. It can't just be the number in front. It can't but just be the coefficient. So in this case, I'm going to assume that it is. Take the square root, sign in the middle, square root, oops, squared. Then I'm going to take the product, 2x times 3y is equal to 6xy, and double that. Do we get the middle term? I'm checking. Oh, no. All right. That means no. Not true. So then I would have to try something else. Now, you guys, most of you learned the AC method in Algebra 1. You multiply the 4 and the 9 gives me 36, or the factors of positive 36 that add up and give me 4. So the answer to this is no. So if the answer to that is no, instead, okay, nothing works. We're going to write then that it is a prime. Prime. It's not factorable. Like that. All right. Part C. I keep putting these in here because you have to remember to check for GCF. In this particular case, I can factor out a 3, so I would do that first. I get 25x squared minus 10x plus 1. Ooh, whoops. I'm a perfect square, and so am I. I'm going to assume and then check, because it's a really quick way of doing it, and then I don't have to do as much work. The square root of the first term is 5x, the sign in the middle, and then the square root of 1 is 1 squared. Take the product of 5x and negative 1 gives me negative 5x. Doubled gives me negative 10x. Is that the same as that? Yes, it is. Okay, we found the answer. That's cool. I'm going to just get rid of this here. So that worked. Okay, I'm done. I don't have to do anything else. Let's say it didn't. I would just stop by taking out the 3, and then I would have to stop there because nothing else factored. But I could factor out the 3. All right, try D right now on your own first, and then we'll chat. Pause the video and try. Okay. You can take out a 5. So here, again, perfect square, perfect square. The only difference is that it's a to the 4th power here. You need to then square root each part. So I still have the 5. The square root of a to the 4th is a squared. The sign in the middle is positive. The square root of b to the 2nd is b squared. Double check. Take the product, a squared, b, and double, do I get that middle term? If the answer to that is yes, I'm done. And the answer here is yes. Okay. The reason why that works, by the way, is that if you took either one of these two, that's why we have to check if it doubles, just multiply it out on a piece of scrap paper for yourself. You should see that we get this right away, right? If I have a plus b times a plus b, first is a squared. Like if I'm using FOIL, outer is a plus b, or a, not a plus b, but a times b. Inner is a times b, and then last is b squared. Oh, look, they're like terms. I can combine a squared plus 2ab plus b squared. Oh yeah, that checks out. That works by multiplying them back together. Okay. Same with the negative. The only difference is when we do the negative one, it's a minus b. Look, I'm going to get a squared. Outer is negative ab. Inner is negative ab. So now they're both, the two middle terms are actually negatives. And then a negative b times a negative b becomes positive b squared. These two combine, we get a squared minus 2ab plus b squared. Okay, that checks out. That's this guy here. So they both work. And that's why we can check. And this is the way we check, is taking the product and doubling. Look here, I take the product of a and negative b is negative ab, and doubling, so times 2, actually becomes that middle term. That's what we're doing when we asked to check. But it just makes the process a little bit faster, but it requires, you must recognize perfect squares. Otherwise, it makes this very difficult for you. I would recommend you having a list of the first 20 perfect squares and the first 10 perfect cubes. So for the first 10 perfect cubes is going to help you for the sum and product of cubes. Now, when you have the sum and product of cubes, this is what it ends up being. It is not a plus b cubed. Like this makes no sense. What you have to then be able to do, if I had, like, for example, here, a plus b cubed, it means a plus b times a plus b times a plus b, and then you would multiply all of that out, and I can tell you it ends up being a cubed plus 3a squared b plus 3ab squared plus b cubed. This is not the same as a squared plus b squared. We need all of these middle terms to cancel out when I do that. And if you're not convinced of that, just multiply these two together first. Once you've done that, get a trinomial, multiply by a plus b, you will see that this is what it'll end up looking like. So that means, how am I going to get all of these middle terms to cancel out? Well, that's what we get here. These are called cubic conjugates to each other, that this times, and then I'm going to, this one here, maybe in blue, here, this. When I multiply them together, I get the sum of cubes. So these are considered, these two here, and the same for the other two, they're called cubic conjugates. Just like we had the regular conjugates, that's for the difference of squares, you have something here called cubic conjugates. And when we multiply them back together, they actually cancel out all of those middle terms. Like if I have a plus b times a squared minus ab plus b squared. Now there's different ways. You can use expanded FOIL for this, or you could just multiply, you know, the a by a squared minus ab plus b squared, and then plus b. So I'm distributing this here over both of these two terms. B times a squared minus ab plus b squared, like that. And then distribute the a and distribute the b. Another option is to do it this way, which some people like doing, is distributing the a plus b over each of the three terms like this. So then I have a squared times a plus b, and then minus ab times a plus b, and then plus b squared times a plus b. So I'm essentially just distributing over those three terms. That's also an option. If I multiply that out, distribute again, I have a cubed plus a squared b minus a squared b plus, minus, excuse me, ab squared plus ab squared plus b cubed. And what ends up happening here, these cancel out. They're like terms. These cancel out. They're like terms. So we're left with a cubed plus b cubed. Now I want you to pause the video and try that for the other set of cubic conjugates. But the reason why they're conjugates are called cubic conjugates is because you get all this cancellation. You end up with a binomial in the end. But in this case, they happen to be cubes rather than squares from before. But when you factor the sum of cubes or the difference of cubes, it must produce a binomial times a trinomial. And for all of this cancellation to happen in here in the middle, I actually need this and this to be opposite signed. Otherwise, all of that middle stuff would not cancel out. Same here. I need this negative and this to be opposite signed. Otherwise, they would not cancel out. And what a lot of people do is mix up what we just did, which is the perfect square trinomials with what we're doing right now, and put in a 2 here. That's also incorrect, because if I put a 2 in there, I would end up having 2's here. And then, again, this would have a 2 here, and this would have a 2 here. These guys would no longer cancel out the middle terms. That's why it needs to be a 1 here, and a 1 here, and a 1 here. So this needs to be a 1 in the middle. I have a little memory device for this. You have like the cube root here and here. Once you have the binomial, we use SOPS, square of the first term, opposite of the product, and then square of the last term. So this is square. This is opposite of product. Ooh, my spelling here. And then square of the last term. So if you notice, you have square of the first term, square, take the product, but take the opposite. The product of A and negative B is negative AB, but the opposite, so I get the opposite sign, so I get the cancellation, and then square of the negative B gives me a B squared. This will always work. So if you determine the first binomial, it'll help you find the rest of it. So if I look at example 4, you have a cube and a cube. And again, having a list of your perfect cubes will be helpful here. So the first thing you're going to do is you're going to determine the first binomial. Take the cube root, x, cube root minus, and then the cube root of negative 27 is actually negative 3. So now that I have this, I'm just going to follow the SOPS. Square the first term, which is x squared. Take the product of these two, but the opposite sign, that's the O, opposite product. So negative 3x becomes positive 3x because it's the product but the opposite sign. Otherwise, all those middle terms would not cancel out. And then square the last term, negative 3 squared becomes positive 9. And you're done. Those are cubic conjugates. For the next one, it's very tempting. 8 is a perfect cube, and so is the 64. However, a lot of people would forget to factor out the 8. It's a GCF. So here, I would just be really cautious. Always check for a GCF first. Like, we're so in the moment sometimes, we forget to do that. Now I have the sum of cubes. Okay, I have the 8. Take the cube root is x. Cube root of 8 is 2. And then we're going to use SOPS, S-O-P-S. Square the first term is x squared. Take the opposite of the product. The product is positive 2x. Take the opposite of that, becomes negative 2x. And then square the last term. If I don't take the opposite sign and I don't keep, like if I accidentally double that middle term, I will not get all that cancellation that I need. For this one, factor out the GCF, 4. Then I have a cubed minus b cubed. Okay, that's basically one of the rules. Not square root, cube root, a negative b, SOPs, square the first one, a squared, take the product but change the sign, so opposite of the product, and then square the last term. There you go. Ooh, for this one, if it's a multiple, if the exponent is a multiple of 3, it means that it is a perfect cube. But here we have 6. That means it's both a perfect square and a perfect cube. Now, the advice I will give you is that you treat the perfect square first, whoops, and then you deal with the cubes afterwards. It'll come out in the wash anyways, and I'll show you in a second why that's the case. But in this case, I would, and it's advice I'm giving you, I would always deal, or else you would miss some factors. I would always deal, if there's 2 possibilities, you could either do perfect or difference of cubes or difference of squares. I would then do the difference of squares first. So I would treat this as the difference of squares first. I would treat it like this, squared minus a cubed squared. Okay, that's going to be my regular conjugates is p cubed minus a cubed and p cubed plus a cubed. This is like a math teacher's dream. You get a 2-for-1 or 3-for-1 difference of squares and both of the sum and difference of cubes. Now you factor completely. So factor completely. So the first one is going to give me a p minus q, no, p minus a, not q, whoops, p minus a. And then use SOPs again, square the first one, change the opposite of the product, PA, square the last term. And then the second one is going to be P plus A, square the first, take the opposite of the product, square the last, like that. If you did it the other way around, if you treated it like this, P cubed, oh, whoops, I did that wrong. P squared to the third minus, and then a squared to the third. I would do it, okay, I'm getting P squared minus a squared, with cube root and cube root. And then SOPs is going to give me P to the fourth plus P squared a squared plus a to the fourth. This factors further, P minus A, P plus A. But this one, it does factor further. It's just that you probably don't have the skills yet. We will get it to factor that further. So look here, this here, and you would miss that. That's why it's my advice to you is to actually factor, if there's an option, factor the difference of squares first. Now, eventually that's not necessary, but what this means here is that these, ooh, I should probably not use green. What should I use, pink instead? That's hard to see. Pink. These two factors is how this trinomial factors. Not super apparent. We're going to use a different technique later on, but that means that you would actually miss one of the factors or a set of factors. So I put this here, NTS, note to self. Currently, if there is an option to do either difference of squares or difference of cubes, start by doing the difference of squares. Otherwise, you may not have factored fully.